So our next lab is about thermochemistry and using Hess's law. So at its core, this is the equation we're going to be utilizing today. The fact that when we think about the heat of a reaction, I want you to think about enthalpy. So enthalpy is a very important parameter to lots of chemical reactions, but one of the things we know is that we cannot measure enthalpy directly. We don't have a scale or a meter that measures enthalpy. So as often is the case in chemistry labs, we measure things that we can measure, and then we use data manipulation as a way to determine the pieces that we're interested in. So in this case, we can measure the heat that's either evolved or taken in by a chemical reaction. We can use that by measuring temperature changes, and we can use that heat then as a proxy for enthalpy. And many chemical reactions, depending on the system and what's going on in the chemical reaction, enthalpy is really largely heat in that process. So that's the core concept of what we're working on today. So we are going to be looking at 3 different chemical reactions. You learned about acids and bases last year, so hopefully you recognize that this first reaction is the reaction of a strong acid and a strong base, generating a salt and water. The next reaction is the reaction of a weak base and a strong acid. And then the last reaction is the reaction of a strong base and a weak acid being NH4+ as part of the ammonium chloride salt. So we're going to be evaluating these 3 reactions. We're going to be asking about the heat that's either evolved or taken in by these chemical processes, and we're going to use that to determine the enthalpy of these reactions. So that's really what part 1 is all about. We're going to be measuring temperature changes for these reactions, and that's an experimental method to determine enthalpy. It's really not even a second part to the lab. It's really part of your post-lab questions. It's actually going to be using an empirical method to determine the enthalpy of reaction 3. So hopefully you've gotten to learn about Hess's law in your general chemistry lecture. At its core, what Hess's law allows us to do is manipulate chemical equations and their associated enthalpies, so we call those thermochemical equations, and we can manipulate them such that we can add things up and get to an overall net equation. So we'll come back to this, but hopefully you can see this. Let's look at reaction 1 that has these 4 parameters. Importantly, note that HCl is a reactant. And if we flip reaction 2, and don't have HCl as a reactant, but HCl as a product, when I would add up reaction 1 and then the flip of reaction 2, that's actually going to give me reaction 3. Write that down for yourself if you're not convinced. But by then taking and adding the enthalpy for reaction 1 and the negative of the enthalpy for reaction 2, I can use that to empirically, or from a calculation standpoint, determine the enthalpy for reaction 3. So this has both experimental and computational pieces, and we're ultimately going to be investigating the enthalpy of this chemical process. Okay, so what are you going to be doing in lab? We're going to be doing calorimetry. So here's our very simple coffee cup calorimeter. Dr. Brown has a great video that allows you to actually see what this looks like in the lab and how you're going to utilize our LabQuest as a way to gather data. But at its core, it's really a large coffee cup that we put our reaction materials in, a small coffee cup that sort of sits inverted with a hole on top, large enough for you to put your thermometer probe, and in general, we're going to assume that very little heat is going to escape from this system. So again, this probe is hooked up to your LabQuest. We've used LabQuest for lots of things. Now we're going to be using it to measure temperature. So we're going to measure the change in temperature as a function of time. So there's going to be an initial temperature that we're going to measure before we mix our reaction materials together. And then you're going to obtain a final temperature by linearly fitting our data. See if this makes sense. You are going to be in this coffee cup mixing 2 liquids, putting another coffee cup on, putting a thermometer probe in, and then pressing play on your LabQuest and hoping that not too much time has passed before your reaction has actually reached its maximum temperature and already started cooling. So I already gave you a heads up there. This is going to be a reaction that generates heat. We're going to heat up the contents of our coffee cup calorimeter. So what you might start seeing is that you have some theoretical maximum point that maybe you miss because of how you're mixing things together. So what we're going to do is we're going to ask the LabQuest to fit the linear portion of this data and we're going to ask it to extrapolate back to when time equals 0, that instantaneous point when we first mix those chemicals together, and that's going to be our final temperature. Okay, so now we have our final temperature and our initial temperature. There's spots in your data table to put these pieces on page 4. And those are going to be the important experimental parameters that we are going to use to ultimately determine how much heat is generated from this process and then correlate that to enthalpy. Okay, so highlighting 3 reactions. Each of these reactions is going to have 25 milliliters of each solution. Each solution is 3 molar. So we're going to have to make sure that we're careful with safety here. Make sure that you're wearing your safety goggles. Certainly not things you want to be splashing on your eyes, on your face, on your skin, and so forth. Couple of other safety things to think about. Reaction 2 is going to be generating ammonia, NH3, as a product that can be kind of smelly. And so what we're going to do is as soon as you have, we're using ammonia in reaction 2, when you go to pour out that reagent to use it, do that in one of those little hoods that we have. Just keeps the fumes from sort of getting too overwhelming in the lab. We're generating ammonia in reaction 3. So as that product is generated, go ahead and put it in a waste beaker that's in the hood. There should be waste beakers that are already around in the hood, and that's going to keep those fumes, again, from being problematic. Reaction 1 and 2 waste products can just go right down the drain. Remember, we're generating, let's flip back here and look, we're generating salt water. We're generating ammonium chloride, so essentially that's a salt. And again, this one's the problematic one because we're generating ammonia in that process. Okay, these 2 can go down the drain. This one, because of the ammonia that we're generating, go ahead and let that sit in the hood and we'll take care of it afterwards. Okay, so you've gathered your data, right? You've got initial temperatures, final temperatures. How are you going to do these calculations? Hopefully this is an equation you've gotten to in lab. This is our calorimetry equation, or our heat capacity equation, that tells us that the heat for a process is equal to the specific heat capacity of the substance, the mass of the substance, and how much it's changing temperature. So I like to think about this when we talk about water, for example. If you have a small amount of water, that is, your mass is small, a small amount of heat will only have a small temperature change. These are all directly proportional. Whereas if you want to have a large temperature change, you're going to have to increase the amount of heat you have. Or if you have a swimming pool versus a coffee cup, you're going to have a lot more heat in order to have the same temperature change. So this equation, I think, is pretty intuitive. So what's going to be a little bit different here is we're not actually using the mass of any substance, and we're not looking at specifically the mass or the specific heat capacity of water or of our coffee cup. We're actually going to be lumping these pieces together, and we're going to use a special number that's specific to our unique coffee cup calorimeter, and it's going to be 210 joules per degree C. What that really says in words is if we want to increase the temperature of the contents of our coffee cup calorimeter by 1 degree C, we're going to need to add in 210 joules of heat. We're going to use this equation to actually calculate how much heat is generated by looking at the difference in our temperature. So final minus initial. Anytime you see delta, that's final minus initial. Okay? So for these 3 reactions, you're going to use those temperature changes to calculate the heat. And I've already kind of given you a hint. It's the heat that's evolved for each of these chemical reactions. What we want to do after that is we want to then calculate the moles of the limiting reactant that we have. You'll see why on the next slide here. We mix 25 milliliters of each solution. Each solution is 3 molar. So we really don't have a limiting reactant. So you can pick either your acid or your base to then use to calculate the number of moles that you have. Okay? Why are we doing this? Well, that heat that was evolved is going to have units of joules or kilojoules depending on how you want to calculate it. We want to contextualize that to the amount of substance that we have. So you're going to take your enthalpy value that you determined in part A there, and you're going to divide it by the number of moles of your limiting reactant that you just calculated in part B. And that's going to give us, for reaction 1, 2, and 3, a delta H value that has units of kilojoules per mole. Okay, we want to have that get reported on the board, and then I will help generate an average, which you're going to use in our next steps. Okay, Part of the empirical calculations part here is what is part of post-lab question number 2. So again, what you're going to have is you're going to have your reaction 1 that's going to give you some enthalpy value, units of kilojoules per mole. You're going to have equation 2 that's going to have some enthalpy value in kilojoules per mole. You'll also actually have a value that you calculate for reaction 3. But post-lab question 2 is going to ask you to determine what this enthalpy value is, not from an experimental determination, but from an empirical method like Hess's law. So again, what that's going to mean is you're going to take this equation and use it as is. If I flip this equation, that means I'm going to change the sign on my enthalpy value, and then I add up these equations. It's going to give me the same equation as I have in reaction 3, and I'm going to then calculate that delta H value empirically. Okay. The last piece here is to think about comparing these different methods for determining the enthalpy for equation or reaction 3 and saying which do we think is best and why do we think one is more error prone than another. So reminding you, you had an experimental method that you used to determine delta H for the third reaction. Everybody else in the class did as well, so then we determined an average value. You then used an empirical method with the data from experimental reaction 1 and reaction 2 to determine delta H for reaction 3 empirically. And then in your lab, it tells you what the truth is, what the actual enthalpy of that reaction is. So you're going to look at all 3 of these values and you're going to say which is most accurate, which one is closest to the truth. And then you're going to try to think about why do you think that is. As a hint, do you remember when we did our lab on freezing point depression? We had a solid that we then measured its freezing point for, or we had a solvent, that lauric acid, that we measured the freezing point for, and then we added and mixed benzoic acid inside, and then we said, how much does that freezing point get depressed? And we actually did some pretty intense calculations to back out what the molecular weight of benzoic acid was. Don't know if you remember that lab specifically, but what was unique about that lab is there was not a very significant change or freezing point depression. That was a fairly small number, such that small deviations in that number from the truth would result in large differences in the calculation of that molar mass. So I want you to think about that in the data that you're going to be getting from today's lab in terms of determining our delta H value. Okay? So that's all that we have for this lab. Pretty straightforward lab, both experimentally and computationally, but will allow us to think about thermochemical reactions and Hess's law.